Okay, in the last video we talked about total internal reflection, and the idea behind that is that there comes a point if light is traveling from more dense to less dense, there comes a point where the angle is far enough away from the normal, the incident angle is far enough away from the normal to cause the refracted angle to be 90 degrees. At 90 degrees, and so that's kind of an important point that you might want to write down, that if you have theta sub c as your theta sub 1, then theta sub 2 is going to be 90 degrees. That's by definition, it's going to be 90 degrees. Well, the whole idea of total internal refraction is an important piece to fiber optics. Fiber optics uses the properties of light, particularly total internal reflection, to carry digital data faithfully and quickly over long distances. You want to be able to carry information at the speed of sound, but you want, or I'm sorry, at the speed of light, oh my goodness, at the speed of light, but you want it to be able to travel at a very specific path and in a very specific speed. So fiber optics kind of keeps the light going in a specific direction, and it doesn't have to be carried through air only like other electromagnetic radiations can be. But if you bury the cable with the fiber optics in it, then you can travel that particular stream of information over very long distances and very quickly, and the information is not going to be degraded at all as it travels far away. And it uses that principle, but being able to pull light together with packaging it with information, with data, makes it super, super functional. All right, the next thing we're going to talk about is prisms. And here is my drawing for prisms. Basically, what I want to show you with this is that if I am shining it onto the hypotenuse, if you want to say it that way, onto the hypotenuse of my prism, then what you do to find out where the inverted angle is, or where the image is going to be that is transmitted through the prism, then you just really draw straight lines until it hits a surface and make a 90-degree angle with that and pull it up. And whatever that particular part is showing here is going to be represented up here. So the base of my light is here, and the base of my candle is here. The tip of my flame is here, so it reflects and becomes, refracts rather, and becomes the tip of my flame here. You may be looking at that and thinking, wait a minute, she didn't show anything about refraction in and refraction out. Well, that's the beauty of going from, in this case, air to glass, glass to air. The refraction in is fixed again in the refraction out, so that you can pretend that they're 90-degree angles, and it works perfectly. So when I do it this way, it is an image that's inverted 90 degrees, but when I shine it, I'll call it the hypotenuse. It doesn't have to be a right angle, but you get the idea. When I shine it from the hypotenuse, and now I'm coming against an angle to the surface, again, it's going to go 90 degrees, go down, and then it's going to go 90 degrees and back out again. And the bottom of it 90 degrees and down, 90 degrees and back out again. And what's happening then with this is that it is getting, it's going to be inverted 180 degrees. So just follow the path of the image and it'll tell you what it looks like on the other side. And the last thing that we need to talk about in this section is dispersion. Dispersion is the separation of light into its different colors. And it all has to do with velocity. All has to do with velocity. So the relationship between speed and a medium, you already know that c is the speed of electromagnetic radiation in a vacuum. And as soon as I throw a medium in there, it absolutely slows down. It slows down as I hit a medium. And I have a drawing that I want to show you, and I need to get the drawing handy here. So give me a second. I've lost my drawing. And there it is. Good. All right, I needed to pull that up to have it. But the optical density and optical density is not like physical density, it's not mass per volume, but optical density is a way of measuring how sluggish a material is in propagating the electromagnetic ray going through it. And the slower it is at propagating it, the more optically dense it is, and the more optically dense it is, the slower the wave will travel through that medium. Optical density is used to determine, I'm just going to say it determines the speed in that particular medium. Whatever medium I'm putting it in. So again, let me say that how the atoms interact with that form of electromagnetic radiation, it causes them to vibrate. And if it vibrates at its natural frequency, we talked about that in the last chapter. It's not a big deal to worry about that again right now. But if it vibrates easily, it's going to be able to pass that form of electromagnetic radiation on right away. If it doesn't vibrate at the natural frequency of the wave, then what it does is it gets the electrons to, within the atom, it gets all of the electrons within the atom to start vibrating until it can pass that vibration on at the right frequency to the next atom. But what happens is it travels at the speed of light between atoms because there's nothing, it's empty space between atoms. And so going between the atoms isn't the big deal. It's how quickly can that atom pick up that vibration, find the right frequency for it, and send it on to the next one. And if it can't do it easily, if it does it sluggishly, then that's called optically dense, and that means it's going to have a very slow speed to it. It's going to slow it down quite a bit. All right, the colors of light. And this is a big deal right here. The colors of light slow down at different rates. This is why you can get a rainbow. And I'm going to pull up a picture that I did before, just because the precision of it was kind of important. And this is the example in a prism underneath. And I'd like you to try to go ahead and draw that somehow in there into your notes, because I want you to see that here I have white light coming in. It hasn't separated yet, it's all traveling at the same speed. But now when I've hit the medium here, this is optically dense enough that it slows it down. Each band slows down enough and dramatically differently that it can actually spread it out. You understand that how much it refracts depends on the speed. That's the whole point between the equation. Here, I'll pull that up a little bit. Sine of theta sub 1 over v sub 1 is equal to sine of theta sub 2 over v sub 2. This is my angle of refraction. That how much it refracts depends on the speeds. Another way of looking at it is n is equal to c over v. The index of refraction depends on the speed. So the slower it is, the bigger the index of refraction. The bigger the index of refraction, the greater it's going to change direction because it's changing speed in the medium itself. But white light then, because it's hit a very optically dense material, is going to slow down pretty dramatically, and each one slows down at a different speed. It slows down differently, so it spreads it out. And then it does that again as it leaves. It spreads it out even more as it leaves. And so that's why you're able to get the colors of the rainbow. It's all about the fact that when it hits the medium, a right kind of medium, like a prism, it's going to slow down as it gets into the medium that is more optically dense. And each color of light is going to slow differently. The different rates of change of speed is going to create different indices of refraction. That's going to spread the light out because they're not all bending at the same angle, because they all now have different ends in my prism. All right, so that's the explanation of a rainbow. You've got everything covered now. This covers the whole spectrum of everything we need to do with light. And you can talk to me about when you want to do a test for this. I'm not in a big hurry. If you can get it in sometime this week, the students are not doing a test. They're doing a presentation in front of their peers. And I had thought about having you guys do a video and have that be your test, where you're doing a presentation of one of the phenomenon of light. But instead of that, I decided for you guys, because that kind of puts you in an advantage that you can video your presentation and they can't. So you can tweak it and fix it, and plus you have to be able to answer questions, and you can't do that in a video. Trying to do it on Zoom would be a nightmare, because then if you do have audiovisual things that you want to be able to do, trying to do it through Zoom would be difficult. So I think with you guys, I'm going to stick with the test. I will tell you that it is a 2-day test. If you want to take it all in one day and get it done at once, that's fine. If you want to do that over 2 days, that's fine. If you get it done by a week from tomorrow, by the end of the day, week from tomorrow, I'm happy. I'm perfectly fine with that. We'll start new stuff this week, but it doesn't overlap with this at all. Sooner is probably better than later, but you work this out according to your schedule, and then just let me know what you're going to decide about that. Okay? Let me know if you have any questions about the homework. Some of the face-to-face students are struggling with the critical angle. You can use sine of theta over v is equal to sine of theta over v. You can use that formula to find the critical angle if you know the velocities. And you just know that your second theta is 90 degrees. So you can use that equation if all they give you is velocities. And certainly you can use that equation for sound especially. But for either of them, you can use that equation. All right, let me know what you need from me. Otherwise, just kind of work through when you want to take the test and get back to me.